These are the lesson activities for section 4.4. Number 1, use coordinates to verify that B, which is a set of 4 quote-unquote vectors, 3 vectors. 1 minus 2t squared, negative 4t plus t squared, and negative 1 minus 2t. So I'm calling them vectors in quotes because vectors look more like this. But vectors, what we've seen now in chapter 4 is that we can expand what it means to be a vector space to things that act like vectors. So these are polynomials of degree 2 or less, and it turns out they are a vector space. So we're supposed to use coordinates to verify that that set is a basis for P2. And a basis, remember, is a linearly independent spanning set. So those 3 vectors, or polynomials, have to be linearly independent, meaning none is a linear combination of the others. And they have to span all of P2. So meaning you can build any polynomial of degree 2 or less by taking a linear combination of these 3. Okay, so hint 1 says P2 is isomorphic to R3. They act essentially the same. So each of these 3 elements in the potential basis corresponds to a vector in R3. So for example, the first element, 1 minus 2t squared, corresponds to the vector 1, 0, negative 2. So we're looking at the constant, the t term, and the t squared term as the first, second, and third entries. Okay, so now I'm going to convert the other 2 vectors, the other 2 polynomials to standard vectors. So I'm going to have 0, negative 4, 1, and negative 1, negative 2, 0. So those 3 vectors, if I can show that they're a basis for R3, then the 3 corresponding polynomials are a basis for P2. So to determine if something is a basis, it has to be linearly independent and span R3. So I would put these into a matrix and row reduce. And what I'm looking for is linear independence. I'm looking for a pivot in every column. And span R3, I'm looking for a pivot in every row. So it turns out that when I row reduce this, I get, 1 second to put this in a calculator, the identity matrix. Okay, so I have a pivot in every row and a pivot in every column, which means these 3, the 3 columns, form a basis for R3, which means that these 3 polynomials form a basis for P2. Okay, now I'm given beta, a basis of P2. Okay, same basis that we just verified. It says find Q given that the coordinate vector with respect to the basis beta is 1, 0, 1. Okay, so the way I remember which direction we're working, whether these are weights or you're solving for weights, is that this notation, the vector Q with respect to the basis beta, these are weights on beta. Okay, so we're going to do this problem 2 ways. Convert each element of the basis into a vector in R3, and then use the entries from the coordinate vector with respect to beta as weights on the R3 vector. Okay, let's do that first. So let's see, convert to R3. So I have 1, 0, negative 2, 0, negative 4, 1, and negative 1, negative 2, 0. Okay. Then it says use the entries from the coordinate vector with respect to the basis beta as weights on the R3 vectors. So I'm going to put a 1, a 0, and a 1. And we'll do this arithmetic out. So I have 1 plus negative 1 is 0, negative 2, negative 2. And finally, convert back to P2. So this, when I convert to P2, would be 0t squared minus 2t minus 2. So that is the Q. We found Q given that its coordinate vector was 1, 0, 1. Another way to do this is to never leave P2. Instead of converting to R3, doing the arithmetic, and then converting back, we can just stay in P2. Use the entry from the coordinate vector with respect to beta as weights directly on the basis vectors of beta. So I would do 1 times 1 minus 2t squared plus 0 times negative 4t plus t squared plus 1 times negative 1 minus 2t. And then we just distribute and combine like terms. So I'm going to have 1 minus 2t squared minus 1 minus 2t, which is negative 2t minus 2t squared. Same thing we got above, except we never had to go into R3. Okay, so for part B, I'm given a polynomial, p of t, 2 minus 4t minus 3t squared. And I'm supposed to find the coordinate vector with respect to the basis beta, same basis we've been using for this past couple of problems. And so that means I'm looking for the weights. What weights do I put on the elements of the basis? So there's my basis, and these are the weights I'm looking for, A, B, and C. What weights do you put on the basis to build the polynomial we were given? So we can choose whether or not to convert to R3. I'll do it both ways. Okay. So if I convert to R3, I'm going to take each of my elements from the basis. 1, 0, negative 2. 0, negative 4, 1. And negative 1, negative 2, 0. And I'm saying what weights should I put on these to build the vector that corresponds to p of t, which would be 2, negative 4, negative 3. So the way I solve this using linear algebra tools is an augmented matrix. Oops. Okay, so we row reduce this, and we're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. Just doing this with technology. I'm not row reducing in my head. 2, 1, 0. So these are the weights. This says A equals 2, B equals 1, and C equals 0. So my coordinate vector P with respect to the basis beta is 2, 1, 0. That's a vector that holds the weights to put on the basis that will build P. So that's how you would do it using the tools that we've developed in this course. Converting to R3 makes it fairly straightforward. If we wanted to stay in P2, I would just be solving Okay, so first thing I can do is simplify the left-hand side of the equation a little bit by distributing. So I'm going to have a minus 2at squared minus 4b plus 4b, minus, that wasn't right, minus 4bt plus 4bt squared minus c minus 2ct equals 2 minus 4t minus 3t squared. Okay, so now I'm going to combine like terms on the left. So my constants, I have an a and a negative c. So I'm going to have a minus c. And then my t terms are negative 4bt and minus 2ct. So I'm going to combine those by adding the coefficients negative 4b minus 2c all times t. And then my t squared terms, negative 2at squared plus 4bt squared. So I'm going to have plus negative 2a plus 4b times t squared. And that equals 2 minus 4t minus 3t squared. Okay, so now to solve for the coefficients, the a, b, and c that I don't know, I'm going to match coefficients, equate coefficients. So a minus c is the constant term on the left, and the constant term on the right is 2. So it has to be that a minus c equals 2. And then the coefficient on t on the left is negative 4b minus 2c, and on the right, it's negative 4. So it has to be that negative 4b minus 2c is the same as negative 4. And then we equate the t squared coefficients, and I get negative 2a plus 4b has to equal the coefficient on t squared on the right, which is negative 3. So now I have 3 equations with 3 unknowns, and I can set up an augmented matrix. Okay, so my augmented matrix would be, looking at my green equation, I have 1a, 0 b's, negative 1 c's equals 2. And then my yellow equation, I have 0 a's, negative 4 b's, negative 2 c's equals negative 4. And then my red equation, negative 2 a's, 4 b's, 0 c's equals negative 3. So you'll notice that this augmented matrix is the same as this augmented matrix. So we're really doing the same process here. And we solve and we get the a equals 2, b equals 1, and c equals 0. Those are the weights. So the coordinate vector with respect to the basis beta is 2, 1, 0. Same answer as we got on the left. Okay, now we're given beta, a basis for R2, 1, 4, and 0, 6. So I have a vector in R2, 2, negative 1, and I want to find the coordinate vector with respect to this basis beta, 1, 4, 0, 6. So that means, what weights do you put on the basis to build 2, negative 1? That's what we're looking for. So I want to know, what weights do you put on the basis to build z, 2, negative 1? So I can just make an augmented matrix, 1, 4, 0, 6, augmented with 2, negative 1, row reduce, and we get 1, 0, 0, 1, 2, negative 1.5. So when I translate this back to equations, this says 1a plus 0b equals 2, 0a's plus 1b equals negative 1.5. So the coordinate vector for z with respect to the basis beta is 2, negative 1.5. Now I'm given the coordinate vector for z with respect to the basis beta is negative 2, 3, and I want to find the z. So this is the reverse of the previous problem. So this time I'm given weights, negative 2 and 3. The weights are given, so I'm just going to put those weights on the basis and I get negative 2, and then negative 8 plus 18 is 10. That is the vector z. The change of coordinate matrix from beta to the standard basis is just beta in a matrix. Okay, so we just put 1, 4, 0, 6. That's my change of coordinate matrix. The reason it's called the change of coordinate matrix is because if you're given coordinates with respect to the basis beta, like up here, okay, and you would like them with respect to the standard basis, which remember is in R2, it's 1, 0, 0, 1. That's our standard basis in R2. So if I'm given the coordinates with a weird basis, right, a non-standard basis, and I want them to be in terms of the standard basis, all I have to do is multiply the change of coordinate basis, the change of coordinate matrix, by the non-standard coordinates, and you get negative 2, 10, which is with respect to the standard basis, 1, 0, 0, 1. So that's your typical left 2, up 10 coordinates.